everybody, welcome to the 10.3 part 2 video, which will be talking about applications or word problems of exponentials and logarithms. And I'd like to start with that compound interest formula that we used to define the number e in the last one. So let me define what all these variables mean first. First, n means the number of times per year that you're compounding your money. So if I came over here really quick, or wrote up here, if I was talking about putting in money annually, that's once a year, so n would equal 1. If I said semi-annually, that happens twice a year, so that would be n equals 2. Other common ones that come up is if I said quarterly, that happens 4 times a year, so n would equal 4. So annually is popular, semi-annually, quarterly. I would also say monthly, and there are 12 months in a year, so n would equal 12. You could also maybe say weekly, where I think you can assume 52 weeks in a year. And you could also say daily, which you could say n is 365. But some banks are only open, they have a couple holidays, so you could say 360 instead, but just to get the idea of all of these. So other than that, P represents your principal or your starting value. The R represents the rate or the interest, which is usually defined as a percent. T represents the amount of time that has passed, and A represents your final value. So to start, let's solve the first couple questions down here. Given $10,000 is invested at an interest rate of 3.2%, find the balance of an account after 10 years if it's compounded quarterly. So if I consider the equation for compound interest, if I see the word quarterly, quarterly means that it's happening 4 times a year. So that means that my n value would be 4. The amount of time that's passing is 10 years. My initial value is $10,000. And my rate is given to me as 3.2%, but as a number, you move the decimal over twice to the left. That's really 0.032. So if I plug these values into the equation, you would have A equals $10,000 times 1 plus 0.032 is my rate, divided by 4 times a year, raised to the 4 times 10 power, which is really 10,000 times 1 plus 0.032 over 4 raised to the 40th power. So how you plug this into the calculator is very important. You could plug it in exactly as you see it, but you have to be very careful with parentheses, because you probably have to put parentheses around this as well. So here's my suggestion. In your calculator, I would suggest using the order of operations. I would work inside out. So I would do the division inside the parentheses first. So we do 0.032, then divide that by 4. Press enter. Then, if you continue the order of operations, the next thing you would do is add 1. And never erase anything from your calculator, by the way. If now you had to choose between multiplication and raising to a power comes next with the order of operations. So we did parentheses first, now exponents, press enter again. Then lastly, multiply that by $10,000. And if you do that, you get an answer of $13,753.76. So I'm going to write that here. So my answer, if I put money in quarterly, would be $13,753.76. So here's where I'd like you to pause. I would like you to do the second one. What if it was compounded monthly? Think about what n is if you're talking about monthly. I'd like you to plug things into your equation, and when you come back, we will see if we have the same value. So please pause now. Okay, in red, here's my initial work. made this to 120th power because I said n was 12. If you plug this into the calculator correctly, your answer should be $13,765.41. The last part of this problem asks, what if we put money in continuously? What continuously really means is, what if we kept putting money in forever? Which really means, what if we kept putting money in infinitely? So that reminds me of what we talked about in the last video, the limit as x goes to infinity. So what I'd like to do is bring your attention down here for a second. Here is, again, the work of Bernoulli. If this is the compound interest formula, sorry about that. If this is the compound interest formula right here in the beginning purple, what he did was he manipulated this equation and wrote it like this instead, with some algebra manipulation. And what Bernoulli noticed is that he recognized the 1 plus 1 over n to the n power. So if I bring you back to our last video, here was our work that defined the number e. And you might remember I plugged all the values into 1 plus 1 over n to the n. And we realized that this eventually converged on the number e, which means if I go back to where we are right now, which is, sorry, little delay, which is right here, what we can do is replace 1 plus 1 over n to the n completely with the number e. And we can keep the p, keep the a, and keep the RT. If you've ever heard of the equation PERT before, this is where it comes from. It comes from the fact that this converges on the number e. And this comes again because we found the limit as x goes to infinity. So that means up here, if I erase what I wrote here, I can write down the equation a equals p e to the RT. So whenever you're compounding continuously, you can use this equation instead of this because e, you're really taking the limit to infinity. We would have a equals $10,000 for p, e to the rate, which is 0.032, and we multiply that times the time, which was 10 years. And so that if you plug that directly into your calculator, you would get a final value of $13,771.28. So it seems like compounding continuously was the best option, but all these values are very close. So yes, continuously the best, but if you don't do that, you could probably still make a little money. So, half-life question. Let Q represent a mass in grams of radioactive radium whose half-life is 1,599 years. Lasts quite a long time, I have to say. This equation here represents the relationship between that and the half-life. And our goal for the first one is to find the initial quantity. And so when I see initial quantity, what that really means to me is that if it's initial, that means that no time has passed. So t equals 0. So if I'd like to find what the initial quantity was, or Q, I'm going to plug 0 in for t. So we'd have 0 over 1599. 0 divided by anything is 0. So Q equals 25 times 1/2 to the 0th power. Based on our exponent rules knowledge and the order of operations, I have to raise to a power first. 1/2 to the 0th, or anything to the 0th, is 1. So my answer is really 25 times 1, or 25 grams. Find the quantity after 1,000 years. Well, I'm going to plug in 1,000 for t. So Q equals 25 times 1/2 to the 1,000 over 1599. And this, in my opinion, is a strict calculator question. You would take your calculator, you would plug in 25 times 0.5 or 1/2 to the, and I would use parentheses here, 1,000 divided by 1599, close parenthesis, press enter, and I got a value of 6.206, or 16.206. That's about 16.206 grams if it's after 1,000 years. So it seems initially we had 25 grams, And over 1,000 years, that's how slowly the half-life moves. We have 16.206 grams left. Not bad. The last question here is when, so we're looking for time, will the quantity be 0 grams? So this time, let's plug in 0 for the quantity. And we're trying to solve for t. Now, what's interesting about this problem is something that comes up later. Now, first, though, if we're thinking about what we can do to move things around, this 25 is multiplying everything. So what I'm going to do is divide both sides by 25. So we have 0 equals 1/2 to the t over 1599. Now, what you will learn very soon is that the best way to solve this problem is actually by using logs or ln's. But at this point, we actually don't need to, because, again, of our knowledge of exponent rules. Here's my base. My base is 1/2, and we're wondering generally what power do we raise that to get 0. So let's think this through. If I raise 1/2 to maybe a negative exponent, the negative exponent is a reciprocal, so it causes this to flip, so my answer would be 2. If I take 1/2 to the 0th, anything to the 0th is 1. If I take 1/2 to the first, that's 1/2. 1/2 to the second, I raise both of these numbers to the second, so that would be 1/4. If I keep going and go 1/2 to the third, raise these both to the third, that will be 1/8. So if I kept going and going and going, would I ever reach 0? Like if I did 1/2 to something large, 1,000, that would be 1 to the 1,000th power over 2 to the 1,000th power. That still does not equal 0. So can I raise a base to anything to get 0? No, I can't. I can't do this. So that means, when will the quantity be 0 grams? Never. Last problem. Students in a math class were given an exam and then retested monthly with an equivalent exam. The average scores for the class are given by the human memory model, where t is time in months. So someone actually figured out this model. Again, pretty impressive. And the reason that t is between 0 and 12 is that's the many months per year. What is the average score on the original exam? So I think this is what it's probably going to say before we start, is the more time that passes, the worse students may do. Let's see if that's what it does say. So the original score, so that means that time has not passed, so t is 0. So we're trying to do 78 minus 17 times the log of 0 plus 1, or 78 minus 17 times the log of 1. Now, let's again use order of operations, do the multiplication first. Let's first figure out what log base 1 is. So let's think that through. Log base 1 really means 10 to the what is 1? Well, any base to the 0th power is 1. So this is completely replaced with 0. So we really have 78 minus 0. The average score on the original exam was a 78%. Not a bad class average. Class average is C+ is usually a decent exam. What is the average score after 3 months? Okay, so that means I'd have 78 minus 17 times the log of 3 plus 1, or that would be 78 minus 17 log of 4. Now this one, I would suggest plugging it directly into your calculator, because log base 4, 10 to a power, does not give you 4. So if you plug this into your calculator directly, which would look like this, so you would do 78 minus 17 times the log of 4, you would get 67.76%. So in purple here, 67.76%. So over time, it did drop about a letter grade. So let's say that I tested you almost a year later. I would like you to pause the video and see what your score would be then. Please pause now. So after 11 months, I got this to calculate to drop another letter grade to 59.65%. Now, I think the solution, rather than giving the same exam over and over, is to definitely test cumulatively. I think that works based on what I've seen this year. So this teacher needs to test cumulatively, I dare say. Thanks, guys, for watching.